Hi all, welcome to this video from chapter 5. Um, in this video we're going to be talking about what I call the most complicated capacitated facility location model that we're going to do. This is a model where we are going to talk about locating facilities. We're going to be locating plants or factories. We're also going to be locating warehouses. So this is the design of the whole supply chain, starting from a supplier all the way to your demand location. So you as a company have the following decisions to make. So you know who your suppliers are, you know where your market locations are. You have the decisions that you have to make are which which manufacturing plants do you open, and which warehouse locations do you open. So you'll have all options for manufacturing plants, you'll have options for warehouse location. In the previous models that we did, we looked at capacitated plant location model where materials went directly from the plants to the market locations and you were trying to figure out which plants to open. But here it's more complicated. We're going to be looking at plants sending materials to warehouses and warehouses sending materials to market, and plants receiving materials from suppliers. We don't know which plants are going to open, and we don't know which warehouses are going to be open either, and that we are going to make all of those decisions within the same model. So this is a pretty complicated model, very likely the most complicated model we'll be looking at in this course. So well, let's get to it. The mathematical model itself, again, it's in the PowerPoint that I put up last week, so you should be able to see that. So there are a lot of parameters here, but I want you to remember that this is an extended version of the transshipment model. So if you remember the transshipment model, we had a single layer. So you had materials going from supplier, so basically materials going from plants to warehouses to market, but here you have 4 steps, and the two of the middle steps, we don't know which of these locations are going to be open. We're going to make that decision. So it is an extended version of the transshipment model. Just like the capacitated plant location model was the extended version of the transportation model, this is the extended version of the transshipment model. So we are going to have supply constraints, we're going to have demand constraints, we're going to have capacity constraints for plants, we're going to have capacity constraints for warehouses, and then we are also going to have transshipment constraints through the plants and transshipment constraints through the warehouses. So we're going to have a large number of constraints, we're going to have a large number of decision variables, and so it's going to be, like I said, decently complicated. So this is what the mathematical model looks like, just to show you what you can expect. So instead of having just one set of y variables and one set of x variables, we'll have 3 sets of x variables and 2 sets of y variables. So let's talk about that. Why do we have 3 sets of x variables and 2 sets of y variables? So each of these parts of the supply chain between supplier and plants, that is one stage of the supply chain. This is the second stage and this is the third stage. Between each stage of the supply chain, you have to make decisions on how your materials are going to flow. So you have one set of x variables here, you have another set of x variables here, and you have a third set of x variables here. So you have xie, xeh, and xhj, let's say 3 sets of x variables. And apart from that, you'll have 2 sets of y variables, one set of y variables deciding which plants are going to be open, and another set of y variables deciding which warehouses are going to be open. So you have 3 sets of x variables and 2 sets of y variables. That's what you see. And so for all of your y variables, you have fixed cost values corresponding to them, and for all your x variables, you have variable costs associated with that. Now for the constraints. So as far as constraints are concerned, a couple of these constraints are familiar. This is the supply constraint, just like any supply constraint that we had. Total supply coming out of any of your supplier has to be less than or equal to supply that is available from the supplier. And then finally we have the final constraint is a demand constraint, and it's saying that the total demand at any demand location has to be fully satisfied. So apart from this, we have 4 other constraints. Now this constraint again should be familiar. This comes from the capacitated plant location model, where all the supply coming out of a particular plant cannot exceed the supply that is available. And similarly, we are also going to write a constraint for the warehouse, where we say all the supply coming out of a warehouse cannot exceed the capacity of the warehouse, because not only are the plants capacitated, the warehouses are also capacitated. You have fixed capacities for plants and you have fixed capacities for warehouse. So those are these two constraints. And finally, we have two other constraints. Now these constraints, we should actually have them as equal to 0 and not greater than or equal to 0. These should again be familiar. These are the transshipment constraints. We are saying that anything coming in to a plant location has to go out of the plant location. Similarly, anything coming into a warehouse location should go out of the warehouse location. So these are the same as the transshipment constraints that we had before. So now that we know what our constraints are and we know what our decision variables are, let's actually look at an example. So here is an example. Here is some data that I have. So this is okay, let me make this full screen and make the data slightly bigger. You can see. So this is the data that we have. These are the three stages of the supply chain. This is the first stage, going from supplier to your plant locations. So you have three suppliers, one in China, one in India, and one in Philippines. And they supply materials to your potential plant locations in China, Japan, India, and Mexico. So you have 4 potential plant locations, and these plant locations are supplied from your suppliers who are in China, Philippines, and India. So this is stage 1, and each of your suppliers has a certain capacity, and then there is a variable cost of transportation from your supplier location to your potential plant locations. Now, from your factory locations or plant locations in China, Japan, India, and Mexico potentially, your materials are transported to warehouses in the United States, and these are the 5 potential warehouse locations. One in Chicago, one in New York, one in Los Angeles, one in Knoxville, and one in Atlanta. Again, we don't know which of these warehouses are going to be open, and we don't know which of these plants are going to be open. That is part of the decision. Now, the fixed costs for opening the warehouses are here, factories are here, and the factory capacities are here. Similarly, the fixed costs for opening the warehouses are given here, and the capacity for the warehouses are also given here. And the final demand is also given here. So the demand for the 7 regions within the United States, you have Northeast, Mid-Atlantic, South, the Midwest, Upper Midwest, Southwest, and Pacific Northwest. These are the 6 regions that we have in the United States, and these are the transportation costs, warehouse and transportation costs from warehouse locations to the demand locations. So we have the 3 stages of the supply chain. We have all the relevant data. So let's actually set this model up. So this model is going to be pretty complicated. We have 3 sets of xij variables as decision variables and 2 sets of yij variables as decision variables. So we're going to have to do all of that, and then we have to write 1, 2, 3, 4, 6 different sets of constraints. So let's set all of that up. So let's go through them step by step. It seems like a lot of work, but it's really not that complicated. Everything that we're going to do, we did in one or the other model before. We either did it in the transshipment model, or we did it in the transportation model, or we did it in the capacitated plant location model. So the different elements from different models, we're just going to put them all together in a single large comprehensive model. Okay. So step 1, let's set up the decision variables. Let's start from here. Clear everything. So these are my decision variables, which represent transportation from your suppliers to the potential plant locations. So those are my first set of decision variables. The second set of decision variables clear all of this. The second set of decision variables, no, this is not going to be fixed cost. This is the open close variable. So this is going to tell me which of these factory locations are open. So if you look at, okay, so let's look at total demand. So total demand, if I add up all the demand, total demand adds up to about 850 million units. Factory capacity, if I add up all the factory capacity, it adds up to 1330 units. So obviously not all of your factories are going to be open. So we only need about we only need enough factories to supply 850 million units. And similarly, warehouse capacity, if you add them all up, the warehouse capacity is 1750. You have a ridiculously large amount of potential warehouse capacity, and we are not going to use all of that. We're only going to use half of it. So again, we need to figure out which of these warehouses are going to be open. So again, as usual, I'm going to color them differently. So these are my Xij variables, and these are the Y variables. As usual, I'm going to give them a different color. So these Y variables, these are going to be 1, 0 variables, which tell us which plants are open. And these are the Xij variables, which tell us how materials are transported from the plants that are open to the, again, warehouses that are open. So let's write the final set of decision variables. Final set of decision variables are transportation from warehouse locations to demand locations. Right. So these are my These are my 1, 0 variables, and these are my Xij. So these are the Y variables, the ones that I have colored in I guess red, and the ones in blue are the Xij variables. So 3 sets of Xij variables and 2 sets of Yi variables. So these tell me which warehouses are going to be open, and these tell me which plants are going to be open. Right? Okay. Now this is where the decision variables are going to be. So now that I have my decision variables set up, I can calculate the objective function. So the objective here is going to be, again, because we have 3 sets of variables, we'll have the objective function will be the sum of 3 different sum product functions. So we can add the sum product function. So the first sum product function, so each stage of the supply chain will have one sum product function. So this is the cost of transporting from your supplier to your plant locations. Oh, oops, forgot the cost of transporting, comma, the corresponding decision variables. That's the first sum product function for the first stage of the supply chain, plus here again I'm going to, so as usual I'm going to include the fixed cost automatically here. I have to write sum product first. Sum product of the variable cost values and the fixed cost values, comma, the Xij and the corresponding Yi variables. Right? So that's the second sum product function, plus, oops, plus the third sum product function for the third stage of the supply chain. So remember, we are designing most of the supply chain here. So third stage of the supply chain, the variable cost and the fixed cost values, comma, the corresponding decision variable. So again, this might look like a lot of work, but we have done this in one stage or the other. Excuse me. So we did something similar with the transshipment model. We did something similar with the capacitated plant location model, where we included the X and the Y variables. We did something similar in the transshipment model, in the sense that we had two different sets of variables. So we had to write two separate sum product functions there. In the transshipment models, you only had two stages to the supply chain. Here you have three stages to the supply chain, so we have three different sum product functions. Okay, so that's the objective function. Let's just take a look at that. So the objective function has three sum product functions: one for the supplier to the plant location stage, the second one from plant location to the warehouse location, and the third one from the warehouse location to the market location. And that's the total cost, and that's what we are minimizing. That's the objective function, right? Next, we have to set up the different constraints now. So let's begin with the simplest one. So we'll do it step by step. So we'll start from the left end of the supply chain and we'll go all the way to the right end of the supply chain. So we're going to begin with supply constraints. We're going to end with demand constraints. All right. So let's begin with the supply constraints. So we have three supply locations in China, India, and the Philippines, and we know what the supply capacity is. Let's write the supply constraints first. Supply constraints. It's the amount supplied and capacity. Oh, oops. Don't want that. Right. So the amount supplied is all the amount that is supplied out of the China, not the China plant, but the China supplier. Remember, the China plant is different from the China supplier. So everything that is supplied out of the China plant, so you add everything that is supplied out of the China plant to all four potential plant locations. That's the total amount that is supplied out of the China plant. And that should be equal to the capacity of the China plant, which is 350 million units. Not the China plant again, China supplier, which is 350 million units. So total amount supplied from the China supplier cannot exceed the supply that's available with our Chinese supplier. Same goes for the Indian supplier and the Filipino supplier. Okay. Right. 350, 290, and 310. So that's the first step, supply. Total amount supplied cannot exceed the supply. So this can be less than or equal to constraint. So you have the first constraint, the supply constraint. After the supply constraint, the next constraint will be the capacity constraint. So let's write the capacity constraint at the plant location. So let's go back to this. So the first constraint was a supplier constraint. The amount that is available to the supplier, that is all you can supply. The second constraint that we're going to write is the capacity constraint at the plant. So each plant has a fixed capacity, and that capacity is only available if that plant is open. So we have to make that decision. So let's write the factory or the plant capacity constraint. So I'll say factory. The factory capacity constraint. So I'm gonna, these are my four potential factory locations. So I have that here. Say amount manufactured and of course the capacity. Let's call this available supply. Okay, so what is the amount that's manufactured in the China plant? So all the amount that's everything that's manufactured in the China plant gets shipped to one of the warehouses. So everything that is made in the China plant and it is shipped out of the China plant to the 5 potential warehouse locations in Chicago, New York, LA, Knoxville, and Atlanta. So everything supplied out of the China plant. This is everything that's supplied out of the China plant. We have that. And this cannot exceed the capacity of the Chinese plant. So what is the capacity of the Chinese plant? The factory capacity itself is 350, but that capacity is only available. So the factory capacity is 350, but that capacity is only available if the Chinese plant is open, if we may make the decision to open the Chinese plant. So we're going to multiply it with the corresponding Y value. If the Y value is 1, then the capacity is available. If the Y value is 0, then the capacity is not available. So again, we did exactly the same thing when we did capacitated plant location model, where we multiply the capacity with the corresponding 0, 1 variable. So this is the amount manufactured and the capacity at each of those locations. So I'm going to copy that down. So the same goes for the Japanese plant. So the Japanese plant, and the right hand side of the Japanese plant constraint is the capacity of the Japanese plant times the decision variable, which makes it open or not, and so on. So those are the four manufacturing constraint for the factory capacity constraint. So let's go back to our picture here. So we wrote the constraint for suppliers and what supply is available at the suppliers. Then we wrote a constraint for which plants are open. Now we are going to write a constraint which is like the transshipment constraint. So essentially we are saying that all the supply that comes from the supplier to the plants has to get manufactured and supplied out of the plants. We are assuming that all the material that comes in will be used in manufacturing, that we will make something out of it, that no material is left at the plants or no material is destroyed at the plants. So this is not true in most real life scenarios. In most real life scenarios, there's always some wastage, some spoilage, something will happen in the plant location. But here, ideally, we are assuming that everything that comes in from the suppliers, all the material that come in, will be turned into goods and sent out to one of the warehouse locations. So there can be nothing left over at the plants. This is very similar to the transshipment constraint. Everything coming in to the transshipment location has to go out of the transshipment location. Similarly, everything coming in from the supplier to the factory locations has to go out of the factory location. So we're going to write a transshipment constraint. So this I'm going to call supplier to factory to warehouse transshipment. So this constraint ensures that all the material that has come from the supplier to the plant gets turned into a final product and then gets supplied to one of the warehouses, that nothing is left over at the plant locations, right? So again, I'm going to we have the same 4 factory locations, but here the constraint is everything coming in should be equal to everything going out. So everything coming into the Chinese plant location, this comes from the first set of decision variables. Everything coming in to the Chinese plant location from the three suppliers in China, India, and Philippines. So that's everything coming into the Chinese plant location, and this should be equal to everything going out of the Chinese plant location. So this is the sum of everything going out of the Chinese plant location, right? Everything coming into the Chinese plant location should be equal to everything going out of the Chinese plant location. Similarly, we're going to write the constraint for Japan, India, and Mexico. So this is everything coming in to the Japanese location. And this is everything coming into the India plant location. And this is everything coming in to the potential Mexican plant location. And all of these should be equal to everything going out. So everything going out of the Japanese plant location, everything going out of the Indian plant location, and everything going out of the Mexican plant location. So whenever you're designing supply chains, in this case we have 1, 2, 3 stages to the supply chain. We can have supply chains that are really complex, that have 5, 6, 7, 8 stages. But always we have to, when you're designing these supply chains, you always have to write constraints that are flow constraints, which make sure that all the material that starts at the supply location ends up at the demand location. Now, obviously, that is assuming ideal conditions. But of course, let's say that based on your manufacturing, your past experience in manufacturing, let's say that plant locations, everything that comes into plant location, let's say 95% of that ends up at the warehouse location. That is a constraint that you could write, where instead of saying everything coming in has to go out, you say 95% of everything that comes in will go out to the warehouse location. So there's a 5% wastage, spoilage, theft, breakage. There are lots of different things that can happen. So you could write the constraint that way, but here we're assuming ideal conditions, that all flow starting at the supplier will end up at the market locations, right? So we are about halfway through with our constraints. So we have the supplier, factory, warehouse, transshipment constraints. We are done. So let's look at the next stage of the supply chain. So we wrote constraints for supply available at the suppliers. Then we wrote constraints at the plants. Then we wrote the transshipment constraints to the warehouses. Now let's write the constraints to see which of these warehouses are going to be open. So we write warehouse capacity constraints. So next we write warehouse capacity constraints. So let's pick up the warehouses. So this is where our warehouses are. Amount stored in the warehouses, and this is the capacity. It's available at the warehouse. So the amount that's stored at the warehouses cannot exceed the capacity of the warehouse, and the capacity of the warehouse is again only available if the warehouse is open. So this is where we're going to make decisions on whether or not which warehouse to open and which warehouse not to open. So amount that is stored at the Chicago plant, everything coming into the Chicago warehouse location, everything coming in to the Chicago warehouse location. So I can either write everything coming in. So because I wrote these as that, I can say everything that is supplied out of the Chicago, because everything coming in should be equal to everything going out anyway. So instead I'm going to write the constraint this way. So everything that is supplied from the Chicago warehouse, everything that is supplied from Chicago to all the 7 different market locations, everything that is supplied from the warehouse cannot exceed the capacity of the warehouse. So everything that is supplied out of the Chicago warehouse, that's the sum of everything that is supplied out of the Chicago warehouse, should be equal to or less than or equal to the capacity of the warehouse. And the capacity of the warehouse is 350, but only if that warehouse is open. So it's the capacity of the warehouse times the variable which decides if the warehouse is open or not. So again, this is very similar to the capacity at plant location constraint. This is the amount that can potentially be stored, and that cannot exceed the capacity of the warehouse. So similarly, I can copy this constraint down. So this is everything that is supplied out of the New York location, and this cannot exceed the capacity of the New York location, which is again 350 is the capacity times the decision variable yi. Similarly, we have the warehouse capacity constraints. That's the next constraint, and the constraint after that, again after we write the warehouse capacity constraint, we have to write demand constraints for markets. But before we get to the demand constraints for market, we also have to write the transshipment constraint through the warehouses. So everything comes, so we wrote one set of transshipment constraints where we said everything coming in from the suppliers to the factory locations has to equal everything going out of the factory location to the warehouse location. Similarly, we had tried a transshipment constraint at the warehouse location which says everything coming in from all the factories to the warehouses should be equal to everything going out of the warehouses to the demand location. So we had to write a transshipment constraint through the warehouses. So let's write the warehouse transshipment constraint. So I'm going to call it factory warehouse market or demand. Let's call it demand. Market transshipment constraint. As you can notice, we've done all of these pieces in different models. Now we're just putting them all together in a large model. It is not any more complicated than what you did before. It's just bigger. That's how it is. So remember, so this, the transshipment constraints we wrote before is supplier to factory to warehouse. So everything coming in from supplier to factory should be equal to everything going from factory to warehouse. This is the transshipment constraint from factory to warehouse to market, which means that everything coming in from the factory location going to the market, everything coming from factory location going into the warehouse location should be equal to everything going from the warehouse location to the market location. So let's write that. So again, we are going to, these are our warehouse locations. So everything coming in is equal to everything going out. Let's write this constraint. So everything coming into the Chicago location, Chicago factory location. So this is everything coming in to the Chicago location from the 4 potential plant locations. That's everything coming in. Similarly, everything coming into the New York location, then everything coming into the LA location, Los Angeles, everything coming into Knoxville, and then everything coming into Atlanta. Everything coming into Atlanta. So everything coming into Chicago should be equal to everything going out of Chicago, and everything going out of Chicago is right here. That is everything going out of Chicago. So everything coming into Chicago should be equal to everything going out of Chicago. So because these are like that, you can just copy these constraints. So everything coming into New York should be equal to everything going out of New York. Everything coming into LA should be equal to going out. Same with Knoxville and Atlanta. So we have the 5th set of constraints, which are the factory, warehouse, market, transshipment constraints. And finally, we have our demand constraints. So we wrote supply constraints, everything going out, plant constraints, which plants are open. Then we wrote a transshipment constraint. Then we wrote a constraint for which warehouses are open. Then we wrote the transshipment constraint. And finally, we had to write demand constraints for the demand location. As you know, I like to write demand constraints as columns. So let's do it the usual way. Okay. Amount supplied. Whoa, it's too much. Let's say demand. So the amount supplied to the northeast northeast demand location. So that's everything coming into the northeast location. Everything coming into the northeast location. So these are again demand constraints, just like any demand constraint. Because I wrote them the right way, I can just copy them out. Is everything coming into Midwest? So if I wrote everything correctly, right, everything coming into the Midwest, then everything coming into Upper Midwest, everything coming, everything coming into Southwest, and everything coming into Pacific Northwest, right? And each of these should be equal to the corresponding demand values. The corresponding demand values are here: Northeast, Mid-Atlantic, South, Midwest, everything. So again, I can just copy these numbers out. There you go. Corresponding demand values: Northeast, Mid-Atlantic, South, Midwest, Upper Midwest, South, Southeast, and Northwest. And there you go. So all our constraints, so the 6 set of constraints are set up. 3 set of xij values and 2 set of yi values are set up. The objective function is set up with the 3 sum product functions. So we have put everything into Excel. The final step remaining is putting it into solver and clicking solve. So let's do that. Let's begin with the solver. So the objective function right here, that's our objective, and the objective is to minimize the total cost of the whole supply chain. This includes transportation from suppliers, manufacturing at factory locations, transporting to warehouse, storage at warehouse, transporting from warehouse to demand locations. All of those costs are included. Essentially, most of the transportation and production costs in the supply chain, and we are minimizing that. And the changing variables, so we have 3 different sets of changing variables here. So we have one set, comma, the second set, comma, the third set. So remember, when choosing these decision variables, do not forget to include the the Yij variables. So you have M4 to P6, that's the first set of decision variables. Then M13 to R16. You have M13 to R16, including the Yij variables, and finally M22 to T26, M22 all the way to T26. So these are all my decision variables. I'm going to change this to simplex LP because this is still a linear problem. Right, so now let's write our constraints. Let's input all the constraints. First constraint that we're going to add is the supply constraint. So total amount supplied cannot exceed the supply that's available. So that's a less than or equal to constraint. That's our supply constraint. It's a less than or equal to constraint. So I'm going to click on add. So total amount supplied cannot exceed the supply that's available. Click on add. Next, the factory capacity constraint. Total amount manufactured at each factory again cannot exceed the capacity of the factory. So again, remember, the capacity constraint has the y variable embedded in it. So I'll click on add again. That's the second set of constraints. Let's write the third set of constraints. These are the transshipment constraints. So everything coming into the factory locations should be equal to everything going out of the factory locations. So everything coming into the factory location should be equal to everything going out of the factory location. Click on add. Then the warehouse capacity constraint. So the total amount stored at the warehouses cannot exceed less than or equal to the capacities of the warehouse. So again, these capacity constraints include the 0, 1 variables that we have. These are the capacity constraints. So again, warehouse capacity constraint, I'm going to click on add. Then the warehouse, then the transshipment through the warehouse constraint. So everything coming into the warehouses should be equal to everything going out of the warehouses. So everything coming into the warehouses is equal to everything going out of the warehouses. Click on add. And finally, we have the demand constraints. So everything supplied should be equal to the demand values. You can click OK. Now it might seem like we are done, but we are not done. We still have to add a couple more constraints. In fact, we have to add one more constraint, which is the binary constraint. We have to specifically tell Excel that our Yij variables are binary variables. So I'm going to choose these variables. So I guess I'm going to do it separately. I'm going to say these set of variables have to be binary values, 0, 1 values. Click on add, and also these set of variables have to be binary variables also. Click on OK. So we have two sets of binary variables, two sets of Y variables, then we have all the other constraints. So we'll have two capacity constraints and one supply constraint. Then we have two transshipment constraints and one demand constraint. Totally we have 6 constraints, and then you have 2 constraints which say that the yi values have to be binary. Then the objective function and the changing variable sets. All of that has been included. So the only thing left is to click solve. Let's do that. Okay. And there you go. All right. So this is our final solution. Now, a couple of things. You'll notice that you have e raised to minus 14 and e raised to minus 14. Those are really small values. They are essentially zeros. So just kind of, oops, not currency, number. So don't worry if you get such a small value, because these are integer values. It sometimes there are some tolerance values. That's all it is. So the value of the objective function is here. So this is our total cost, which is $1,445,795. That's the cheapest way in which you can do it. Now let's see what the supply chain looks like. So factory wise. So we already have that. We also have this here. Let me make this number. Okay. So the Chinese supply location, the Chinese plant sends supply to the China plant and also to the India plant, while the Indian plant sends all its supply to the Mexico plant location. So which plants are open? The Chinese plant is open, the Indian plant is open, and the Mexican plant is open. The Japanese plant is not open, so nothing gets sent to the Japanese plant, as you can see here, because we wrote our constraints properly. And which warehouses are open? The Chicago warehouse is open. The New York and the Los Angeles warehouses are not. The Knoxville and the Atlanta warehouses are open. So we have Chicago, Knoxville, and Atlanta. Those are the 3 warehouses that are open. And you will notice that because these warehouses are not open in New York and LA, all of these values are 0, saying that nothing is supplied out of these warehouses. Similarly, nothing is supplied to these warehouses because those warehouses are not open. Now, capacity wise, so let's look at the capacity constraints. The Chinese plant has a capacity of 350 and we're using only 250 million units of that, while the India and the Philippine plants, we're using up all the supply available in the India and the Philippine supply locations. Now, let's go to the plants. We are not opening the Japanese plant, we are opening the Chinese plant, the Indian plant, and the Mexico plant. We are using all the capacity at the Chinese plant. We are using most of the capacity at the Mexico plant. Now we're just not using 10 million units, but the Indian plant we are only using half the capacity of the Indian plant, right? We also have these numbers here. So. Now, the Chicago and the warehouse, now let's look at the warehouses. As far as the warehouses go, we know that the New York City and the Los Angeles warehouses are not used. And capacity wise, we are using up all the capacity in the Chicago warehouse. We are using all the capacity in the Atlanta warehouse, but we have 200 million units of capacity available in the Knoxville warehouse. That's what you have. And finally, all demand is satisfied in all the different regions. Obviously, that was going to happen because total supply is obviously more than total demand, so all demand will get satisfied. And the minimum cost for doing this is $1,445,795. Now, I will say this. This is a large problem with a lot of integer constraints. So, it is possible that this answer is wrong for me. And the reason I'll say that is I have a Mac. Sometimes, rarely, I'm not saying every time, sometimes, rarely, when you use a solver in the Mac only. With Windows, it usually works 99.99% of the time. With Mac, it is more like 95-96% of the time. You'll get the right answer, but once in a while, you'll end up with the wrong answer because of the way the solver has been written for the Mac. So just keep that in mind. If you get a slightly different answer, that's okay. As long as you've written all the constraints and everything correctly, I will still give you credit for it, but it has to be close. If it's far, then I'm not going to consider that. But yes, so this is the largest supply chain that we have designed so far. This has our suppliers, it has our plant locations, our warehouse locations, and our market location. So it's a full supply chain, and this is how you design that supply chain, right? So this is already a longish video, so I'm gonna take a break here. If you have, again, I'm going to post this PowerPoint, not the PowerPoint, I'm sorry, post this Excel sheet online. So if you have any questions, you can absolutely take a look at that. Anyway, so right, so make sure that you do this week's problems. So this time it's not going to be a case problem per se. I'm also going to give you other problems that you have to do, like a case problem. So just keep that in mind and solve the problems. Right? Take care.